Hello, everyone. In this video, we're going to start chapter 14 with section 14.1, obviously. And we're going to be starting material that really is going to be kind of the basis for the remainder of the course, multivariable functions, or multivariable calculus. And if you have the physical textbook, you might see on the cover, it says multivariable calculus. So let's dive right in. So let's start with kind of a recap of what we've talked about so far in our calculus courses. In Calc 1-2, we had our functions of a single variable. Oops, excuse me. Okay, our functions of a single variable. Okay, so that would be like a function f from the real numbers to the real numbers. So meaning we plug in a single number and we get out a single number. Okay. And then we just did chapter 13, okay? And this, in chapter 13, we covered vector valued functions, right? So we plugged in a number and we got out a vector, okay, in Rn. And now in chapter 14, we're gonna do the opposite of this. We're gonna have functions from Rn to R, okay? Meaning, there's a couple ways to think about this, but you could think about this as plugging in a vector or a point and getting out a single number. Okay, so these types of functions we call multivariable functions. Why? Because they have the form like how we're usually going to see them is like f of x y equals z. Okay, meaning I have two independent variables. That's going to be the standard for this course, two independent variables. Again, this is something that works in any dimension greater than one, really. If n is greater than one, it's a multivariable function. So we could have two independent variables giving us a dependent variable, or we could have like a function of three variables giving us a fourth dependent variable, or we could have just a whole ton of variables. And what you'll see a lot of times, like if it's a function from R2 to R, you'll see f of xy equals z. And then if it's a function of three variables, maybe you'll see f of x, y, and z equals, something. And then if you start getting into, we're running out of letters, obviously. So if you start working in higher dimensions, a lot of times instead of x, y, and z, we'll use x1, x2, x3, x4, and so on. So if I have like, I'm going from R5 to R. Okay. Maybe I would have something like this. Okay. So these are my independent variables. And then y would be my dependent variable. Okay. Again, so I'm trying to show you guys as much generality as possible. We are going to be mostly concerned with just this case here, f of x, y equals z. And so that's the notation you'll see a lot. Okay. So let's go ahead and give a informal definition of these multivariable functions, similar to what we've seen in Calc 1 and pre-calc, things like that when we first started talking about functions. A multivariable function, f from Rn to R, is a mapping or, a rule, same thing, that pairs each point or vector in Rn to a unique number in R. And we can, have functions. Maybe our function won't be defined on all of Rn. Maybe it's just going to be on some subset D of Rn, which will be the domain. but we'll talk about that later. Okay, but this is kind of a nice first definition for our multivariable functions. So we've already seen this notation, but just to reiterate, we're usually going to be looking at functions from R2 to R, which we might see written like this: f of xy equals z. And z we can think of as just some number that depends on x and y. Okay, so I gave this example, I think, in the kind of first intro video of the course. You know, maybe I'm a jeweler and I'm making a bracelet out of gold and diamonds, and I'm trying to decide how much to charge. Well, how much I charge maybe depends on, you know, the cost of my supplies, right? The market price of gold and the market price of diamonds. So I can think of like, okay, if Z is the price I'm going to charge for my bracelet, maybe that's, you know, some function of the market price of gold and the market price of diamonds, something like that. And then this section 14.1 in your book is just full of examples. There's definitely some material in 14.1, but you know, it's just got plenty of examples, which I think is great. So to supplement this lecture video, I'd definitely go and look at the textbook. You know, you should be doing that anyway, I think. And look at some of these examples. Okay. Now, as we said, okay, before, I already kind of use this terminology, but when we have these multivariable functions, okay, this x and y, those are my inputs, right? So those are my inputs of my function, and my z is my output. So remember from previous courses, these inputs we call the independent variables, right? And then this output depends on those, so we call that the dependent variable. Okay. So we've kind of talked a little about, you know, a little bit of the concepts of multivariable functions, but let's actually look at one. Okay. So these are the same thing, right? I have f of x and y equals x squared plus 3 to the power x ln of y. And, you know, we could just replace that f of xy with that z. Okay. So two different ways to write the same thing. This is a function of Rn from Rn to R, or R2 to R. Okay. So compare that with well, let's compare it to a couple things. Let's compare that to what we maybe saw in Calc 1 and 2. Okay. We had f of x, maybe we had something like f of x equals, you know, x squared plus 4x plus log of x, something like that. Okay. This is a function of a single variable, right? Meaning on this right side of my equation, the only variable that shows up is x. Okay. Everything else is just what? It's just actual numbers, right? I got my x is my variable, and then I'm just doing stuff to x. I'm manipulating x. Okay. As opposed to multivariable functions where I can have x's and y's on that side of my equal sign. Okay. And I think it's also worthwhile to compare this to what we did in chapter 13. Okay. So let's see, I'm plugging in x and y into the right side of my equation. But what am I getting out? Well, let's see. X squared, if I plug a number in for x, that's just going to give me a number. That's just going to be a number. And I'm plugging in something for y, and that's just going to be a number. So I have a number plus a number times a number. So the result is just going to be a number in on my real line somewhere. Okay. And then we can compare that to what we did in chapter 13. It was kind of the opposite, right? I plugged in a number for t, and what I got out was a vector. Right? I got out this three-dimensional output, this vector. So it's kind of the opposite of what we did in chapter 13. Okay. Now, this stuff, these multivariable functions, we've seen some of them before actually in section 12.6, and we're going to talk about that a bit later when we just start talking about graphing. But some of the stuff we saw in 12.6 are actually these multivariable functions. Okay, so we're going to kind of loop back and talk about 12.6 just a little bit. And some of the stuff we saw in that section were functions, and some of it was not. So we're going to make clear what exactly in 12.6 was a function and what was not. Now, I already kind of mentioned this idea of domain. Let's talk about domain for a second. So again, from Calc 1, okay, for maybe a function from R to R, okay, we had this idea of domain, right? Like sometimes this function f is not, sometimes it is defined on the whole real line and sometimes it's not. So for example, if f of x was equal to 1 over x minus 2, I could ask myself, okay, where's this function defined? What's its domain? And if you recall how to do that, you would see that the domain of this thing is this, right? Everything except positive 2. Okay, so these points are all the points where this function makes sense. Okay, all the values we can actually plug into our function and get a meaningful result. Okay, and then these functions have ranges too, right? So let's use a different example. How about f of x equals x squared? Okay, well now the domain of this thing is all real numbers, right? Negative infinity to infinity. Because there's nothing going wrong when I plug values of x into this x squared. I can plug any x in there I want. But what's the range? Okay. The range, so remember, what is range? Range is essentially the outputs of my functions, right? So if, okay, this is my x and this is what my y. My x's are my inputs, right? My y's are my outputs. And this is the graph of my function. Okay, so what outputs do I have? Well, all these are outputs, like everything along my y-axis, my positive y-axis is an output. Because like for this x, okay, I get that y, okay? And I'm getting all of these y's at various points of x. But what about the y's down here, right? There's no x on my real line that I can plug in and get a negative y for this function, right? So my range for x squared is just, let's see, 0 to infinity, okay? Now, just like with those single variable functions, we can talk about domain and range of multivariable functions. And really the concepts, I mean, they're very similar. It's just where our functions make sense, where they don't break down. So we're looking out for the same problems. Usually when we're talking about domain, what are we concerned with? We're concerned with, we don't want division by 0, and we don't want logs of negative numbers. Or, well, how about we don't want logs of 0 or negative numbers. Those are usually the things we have to look out for when we're talking about domains. Okay, so let's do some domains and ranges real quick, just some examples, and these are just straight from the textbook. Okay, let's just stick with domain in these. Domain is usually a lot easier to find than range. Range takes a little bit of imagination, I guess. Not, you know, domain is usually you can just look at the equation and kind of look for these kind of problems. Range, you have to think about, okay, exactly what values would I be getting out of this function? All right, so let's just do domain for these two. What can go wrong? Let's see. Oh, and another thing I don't want to do, I don't want to do square roots of negative numbers, right? We can do square roots of 0, but we can't do square roots of negatives. Okay, so that's another thing to look out for, which we see in this first example. Okay, I have square root of x plus y plus 1 over x minus 1. Okay, so what's everything that can go wrong with this function? Okay. Well, first of all, I have division, so I don't want to divide by 0, right? So I can see right off the bat that, well, x can't be equal to 1. All right. Now I look at the numerator. Well, I don't want x plus y plus 1. I don't want that to be negative. So I have this inequality, x plus y plus 1 is greater than or equal to 0. Okay. Now, this is not enough, and sometimes you'll be asked to actually graph the domains. Okay. So what's the difference between these domains and domains we've seen before, right? Domains for this single variable stuff, the domain was just, maybe it was the entire number line, or maybe it was pieces of the number line. But our domains were like, we could think of them as like shaded regions of my number line. Like, so for this example, if this is 2, my domain was the shaded region of everything except 2, right? We could think of this in similar terms. Okay, we have these kind of two conditions, but it's not enough to write the domain like this. So think about it in terms of the xy plane. So our input is, instead of having a single number input, our input is now x and y. Okay, so it's two-dimensional. Okay, so x equals 1. What does that look like in R2? Let's see. If this is 1, x equals 1 is just that vertical line, right? Okay. So our x cannot be equal to 1. And then what's x plus y? X plus y plus 1 is greater than or equal to 0. Okay. What is that? Well, if we had equals 0, that's just a line, right? And we can kind of rearrange this. Okay, that's the line, y equals negative x minus 1. Okay, so if I had an equal sign, I would just have this line here. All right. But since I have a greater than or equal to sign, essentially what I have is I want all the points, think about, I had, if I have a greater than or equal to sign here, I would have had a greater than or equal to sign, greater than or equal to sign there. So I have y is greater than or equal to negative x minus 1. Okay, what does that mean? Well, what y value, let's say this is kind of my boundary. My x and y's that satisfy that boundary, or that satisfy this inequality, would be everything above that line. Okay, so we have everything above this line, including that line, right? Because we have greater than or equal to. All right, so I have this whole shaded region, but I don't have, I want to avoid that line x equals 1. Okay, so my domain should be everything above this sloped line and not equal to that blue line. Okay, so that's my domain. Okay. And just like with functions of a single variable, sometimes we want to put that together in a nice, neat notation. So we don't have intervals in R2, right? Like on the real number line, we could write our domains in interval notation. Like if our domain was -2 to 2, maybe those endpoints aren't included, I could write that as this interval, right? But we don't have intervals in R2 and R3 and beyond. What do we have? We just have general set notation. So another way I could write this is I put a brace. Okay, I put braces. All right. And then I'm going to put, in my braces, I'm going to put X, Y. Okay. And this is just kind of like you're saying, okay, we have these points, X, Y. And then you put like a colon or a solid line. And this is like saying such that. And then you have a condition over here. The conditions your points X and Y have to satisfy. Okay. So what conditions do our X and Y satisfy? We have these, right? These two conditions. So I put those two conditions here. And I separate them by commas. And I put another brace on the end. So this is kind of the analog we have for interval notation. So putting it all together, what does this all mean? Our D, our domain, is the set. That's what these kind of braces are. It's set notation. So our domain is the set of all X and Y's such that X does not equal 1 and X plus Y plus 1 is greater than or equal to 0. So that's how we interpret this notation. All right, so let's try and find the domain of this second example, example B. Okay. Some of this stuff, a little distracting. Okay, so let's try and find the domain and range of B. Okay, so what could possibly go wrong with B? Well, we have a log, so we don't want that stuff inside the log to be 0 or negative, right? So for that log, we want y squared minus x to be greater than 0, strictly greater. Okay, nothing can go wrong with x, so this is the only condition we have to keep an eye out for. So if all we had to do was write that set notation stuff, we could say, okay, well, our domain is going to be what, the set of x and y's such that y squared minus x is greater than 0, which we could also write as such that y squared is greater than x. What if we were told to graph the domain? Okay, so let's try that again. So what you do is you start, you look at your condition and kind of turn it into, instead of like if it's an inequality, turn it into a equal sign. Okay, so let's pretend, so this is our condition. Let's pretend for a second we had y squared minus x is equal to 0. We could graph that, right, in R2. Okay. All right, so what does that graph look like? Well, it's the graph y squared equals x. Okay. In other words, x equals y squared. Well, that's that sideways parabola, right? Okay, so that's what we have if we had an equal sign there. But we don't have an equal sign. We have a greater than sign. In other words, we have y squared is greater than x. Okay. Now, let's see. I have this point on the curve, right, on that graph. Let's say this is 4, 2. Okay. Now, my points that I can use for my graph or my domain are the points x, y, such that y squared is going to be greater than x. So for example, if I was considering like stuff on this line, okay, is my domain going to be above or below that point? Well, I want my y value when I square it to be greater than x. So like, for example, if my y value was 3 squared is 9, that's greater than that x value 4. Okay, so this point's in the domain. And then all these other points are in the domain. And then I can do a similar kind of thought process all along this graph. And I see that my domain is going to be everything outside that parabola. Okay, everything outside. Okay. Going off to infinity in all directions. Just not inside the parabola. And not on this boundary either, right? We have a strict inequality. So I do not want to include the parabola itself either. Okay. So the white shaded region is my domain. Let's do one more example, and then this is a good one because it kind of it's the last remaining case out of these three things. I guess we did a square root already, but let's do one again. This one's interesting. And we can do domain of this, or excuse me, we can do range of this as well. Okay, so we have f of xy equals square root of 9 minus x squared minus y squared. First of all, let's do domain. What can go wrong? We have a square root, so we don't want to take square root of negative numbers. So we want 9 minus x squared minus y squared to be greater than or equal to 0. In other words, 9 is greater than or equal to x squared plus y squared, which I could, if it helps, I prefer to write my inequalities like this. Same thing, right? Except I like having my variables on the left side. All right. So I'm working with this inequality. Okay, what is this inequality? Well, again, let's try and think about this graphically. If I just had to write set notation, okay, I could go ahead and do that. My domain is the x and y such that x squared plus y squared is less than or equal to 9, right? Okay, so if I just have to write set notation, that's fine. But if I'm asked, if I need to get a picture, and drawing this picture of the domain really helps to kind of get some intuition of where your function exists. Okay, you need to, it's good to be able to picture this stuff in your mind. Okay, what is that actual domain? What does it look like? So once again, I do my little trick of changing my inequality to an equal sign. If I had x squared plus y squared equals 9, what is that? Well, that's a circle with radius 3 centered at the origin, right? Okay, but so that's my equals, but I have less than or equal to. So are my x and y's going to be inside the circle or outside? It's going to be inside, right? So my domain is this shaded region, including the boundary. Okay, so that's my domain. Range. What could my range be? My range, this one, might be a little weird to think about, but what helps to think, if you have like a finite region like this, think about what's going on the edge and what's going on kind of in the center. Okay, so like on my edge, like if I took a point, let's say I took this point here, which is the point 0, 3, right? And I plug that into my equation, what do I get? I get square root 9 minus 0 squared minus 3 squared. In other words, I get square root of 0 is 0. Okay, so at this point on my edge, my function is going to be equal to 0, and I can see that at all points on my edge, my function is going to be equal to 0. Then if I plugged, if I let 0 be equal to x and 0 be equal to y, well, my function would then be 9 minus 0 squared minus 0 squared is equal to square root of 9 is equal to 3. Okay, so at the exact center, my function is equal to 3. And, you know, that's not very rigorous, but maybe that means our range is going to be everything between 0 and 3. You know, when I asked for range, I was getting ahead of myself a little bit. If you could graph this, you would see that range is accurate. And we're going to talk about graphing in a minute. Maybe we'll circle back to this example after we try some graphing. With that being said, let's go ahead and, well, let's try one more example of finding the range of something. Just a quick, easy example of finding the range of something. Let's say I had f of x, y equals x squared plus y squared. Okay, what's the range of this thing? We'll see that one easy way to do this is to graph, which we'll talk about in a second. But you can just do this mentally. All right. So if what x and y values can you plug in here? Well, you can plug in any x's and any y's, right? So my domain is all possible x values, all possible y values. How could we write that? Well, we could just write the domain as all of R2, meaning all the points x, y. You know, if we wanted to do a lot of extra writing, we could say we could also write it like this, right? All right, so I could plug any x's and y's into here, but what am I getting out, right? No matter what numbers I plug in, I'm going to get a positive number out, right? So if I plug in, you know, -8 for x, that's still going to be positive. Same thing for y. No matter what I plug in for y, that's always going to be positive. Okay. So let's see, what's the lowest number I could get? Well, if I plug in 0 for x and 0 for y, then my output is going to be 0, right? And then if x's and y's are anything else, my answer is only going to get bigger. So maybe we can see that my range will be what? 0 to infinity. Okay. So notice that my range is an interval. It's just, so my range is, my output of this function is just a real number, right? So when I'm talking about ranges, my ranges are going to be just somewhere on the real number line, right? So in this case, my range would be everything to the right of 0, including 0, which in interval notation, we would write like that. Okay. Now, let's talk about visualizing and graphing these functions, and that's really going to help. You know, if this is not making sense, you know, input output wise to you, adding in the graph component will probably help you. Okay. So maybe your problem is you can't visualize stuff. All right. So let's talk about how to visualize these functions, multivariable functions. Now, and let's kind of go through with our kind of hierarchy of stuff we've learned. Okay. Starting with the stuff from Calc 1 and 2, and you know, and even before that, functions from R to R, these single variable functions. Okay. What was my input for those functions? Well, it was just some number on the number line, right? What was my output? It was also a number on the number line. Okay. So if I think of input and output separately, I could think about them like this. My input is, you know, just a number line, my output's a number line, and my function f is like, you know, a little rule that takes this x and pairs it up with that y. Okay, so that's one way to think about it, and that's great and all, but we have this even more convenient way to think of it. We kind of put, instead of having two separate number lines, we kind of draw them as one plane, right? And that's really what this plane is, right? Like this is a number line for x, and this is a number line for y. And so when I graph my curve xy, it's like saying, okay, I'm pairing this x up. Let's make this a bit bigger. Okay. So when I graph my function, this graph is saying the same thing. It says, okay, I'm going to take this x, I'm going to pair it up with that y. Okay, that's all that's saying. That's what this, you know, this shape of, or that's what this graph is saying. Okay. All right, and maybe you think of it like this. Maybe you think of, you know, functions like this. They're kind of two-dimensional graph. Okay. Now, before I go further, okay, we don't really have any hiccups here. Everything's going smoothly. When we get to this case, our second case, the case of the stuff we did in chapter 13, things are a little bit different. What is, you know, we throw this term graph around a lot. Okay. And you might think of the graph, when I say graph, you might just think of a drawing like this. Okay. And it's not completely wrong. What is this picture saying? This is saying that we pair up, you know, this x with this y. Okay. So in other words, we have some kind of pairing like this x goes with that, this x goes with that y. And really, that's what a graph is, okay? Where x is the independent variable and y is the dependent variable. Technically, a graph, you know, is not a drawing. It's not the physical drawing of that. It is just this pairing, okay? This pairing of an independent variable with a dependent variable, okay? Now, that's kind of important for this next idea. Okay. What was going on with our stuff in chapter 13? Okay. Let's kind of go down the list again. Input, output, graph. Okay. Well, what was my input here? My input was some number on the number line, right? And my output those were points in R3. And then my function was like saying, okay, I'm going to take this t and pair it up with, you know, maybe I had a curve in R3. It's like saying, okay, I'm taking this t and pairing it up with this x, y, z. Okay. And that kind of corresponds to this idea we had, you know. So what those curves we drew in chapter 13 were not graphs in the technical sense. You know, you might have thought to yourself, okay, I'm graphing this curve, when we had something like, for example, when we had r of t equals what? Cosine of t, sine of t, t. Okay. And you went into the three-dimensional plane and you kind of drew this thing. And what did that look like? It was kind of this spiral, right? That kind of went along our z-axis and spiraled up. So you might have thought to yourself, oh yeah, I'm graphing this thing. You know, that's what I did. But really what you were doing is you were just drawing the outputs. Like this is all outputs, right? This is not inputs and outputs. This is just outputs. If we wanted to draw inputs with outputs, you know, kind of like here where we had one-dimensional input, one-dimensional output, and a two-dimensional graph, okay? If we wanted to graph this thing, we have a one-dimensional input, a three-dimensional output, and we'd need like a four-dimensional graph, okay? So we didn't actually, you know, graph inputs in relation to outputs, right? We just kind of, we had this R3, and all we did was draw the outputs. Okay. So that's what was going on for these vector valued functions. Okay. Now, what is going on? What's going to happen? What's going to happen with the stuff in this chapter? Okay. Now, let's see. We're going to confine ourselves to the case of functions from R2 to R. Okay. If we stick to R2 to R, things are going to work out nicely. Okay. What is the input? The input is a point in R2. In other words, a point in this XY plane. Okay. What is the output? The output is just a real number. Okay. In other words, I'm going to take this point XY. I'm going to pair it up to this number Z. Okay. Can we kind of take this two-dimensional thing, this one-dimensional thing, and put it together to get a graph? Yeah, we get this three-dimensional graph. Okay, and instead of trying to draw it on that right side, I'm just going to draw it down here. So we're back in R3. Okay. And let's see, this is my x-axis, y-axis, z-axis. So my inputs are coming from somewhere in this horizontal plane, right? You know, this square horizontal plane. And where are my outputs? My outputs are going to be somewhere along the z-axis, right? So let's say I'm taking this point and I'm pairing it up with some z value. Okay, so let's say this is the point, let's say 4, 1, and I'm pairing it up to the z value of 5. Okay, so this is my input. And then I just, when I'm graphing it, okay, the graph, let's say my function takes the point 4, 1 and pairs it up to z value 5. Okay, thinking back to my technical definition of a graph, right? It's independent variable, dependent variable. Okay, so what's my independent variable? It's that, you know, 0.41. And what's my dependent variable? It's that z value 5. Okay, so my graph at that point, my graph would be 415. Okay, so there's 41. This is actually 410, right? And 415 is maybe up here. In other words, I've taken this point 41, you know, this 0.410, I could think of that as just the xy value 41. So I've taken this xy value of 41 and I've paired it up to the z value 5, and I put that all together in a single graph, and I end up in a graph, and I get the 0.415. Okay. And I can make this pairing for all the points in that horizontal XY plane. Okay. So maybe I graph that 4, 1 to 5, and I graph this this XY point, I graph it to this Z value and so on. And I graph all these points to Z values. And what do I start to get out? Well, maybe you can picture it. You start to kind of get out this surface, okay, that's kind of hovering above the XY axis, or maybe it goes down and hits the XY plane and so on. But it's a surface. It's not just a line. It's a surface, kind of like we saw in 12.6. So it's kind of like this blanket draped over a shape, if you want to think about it that way. So it exists in the three-dimensional space R3, but this surface, you can kind of think of this as like two-dimensional. Right? It doesn't have any thickness. It's just like a sheet. And that's what a graph of a typical multivariable function would look like. Okay. And you can always think of like little lines kind of going from your surface down to the XY plane. So maybe this point here is on our curve, and we can always think about that like kind of little line that drops straight down to the XY plane. That's like saying, okay, we're pairing, we have this X, this point is going to be what? This would be like something like 0, let's call it -1, 4, 0. And this would be -1, 4, 3. That's like saying, okay, I'm pairing this point, this XY point, -1, 4, up to that Z value 3. And you put it all together in the graph and you get -1, 4, 3. So that's one way to think about these graphs. All right. So that's how to think about them. How do we actually graph them? Well, we actually already know how to graph them. We did this in 12.6. It's just you weren't told at the time, or maybe not in the book. Maybe I mentioned it in the lecture videos. You weren't told at the time those were multivariable functions. And not all of them were. We're going to talk about that as well. So what happened in 12.6? We had a bunch of equations, right? Equations, and these equations had 3 variables. So I had equations like this, right? And then some looked a bit different. Some were, okay. So I had various equations. All of these equations gave me surfaces in R3 that we saw how to draw. But some of these things are functions from R2 to R, and some of them are not. So let's look at the difference. Okay. Well, before we do that, let's talk about graphing a little bit. So we've seen the graphing techniques in 12.6. So there's really no new material as far as graphing these multivariable functions go. Okay, so domain, let's find domain, range, and the graph of h of xy equals x squared plus y squared. Okay. Well, domain and range we've kind of talked about already. Okay, domain of this domain, well, you can verify this yourself. Okay, domain is all of R2. The range is from 0 to infinity. What's the graph look like? That's kind of what we're talking about now, right? Graph. Okay. I've said that you know how to graph this already. Maybe it's clear to you, maybe it's not. You have hxy equals x squared plus y squared. If you want to use the 12.6 material, which is what you need to do, just replace hxy with z. Same thing. Okay. Now what is this? Okay, we're saying z is equal to x squared plus y squared, and we've seen this in 12.6, right? In 12.6, we saw that this was what? An elliptic paraboloid. Called something like that. So we can use our 12.6 material to graph this thing. No. So you guys should be able to graph. This is a fairly simple graph. It's one of my preferred examples. The graph of it looks something like that. So we already know how to graph these. So everything, I won't say everything, but most of the stuff you're gonna be graphing in the homework for this, or like choosing the graphs of the homework for 14.1, and if you do any extra problems, the graphs you're gonna be asked to draw, you already know how to draw them. It's from 12.6. Okay. Now, what I said a second ago, some of the stuff in 12.6 were these multivariable functions, and some of them were not. So once you're comfortable, maybe pause and practice graphing these. Just refresh yourself on the 12.6 material, basically. And once you're kind of comfortable with the graphs, and maybe you can picture them in your head or draw them out, now we can talk about what is and is not a function from that 12.6 material. Okay. So let's go back to let's see what our Calc 1 and pre-calc material. In Calc 1 and 2 and all that, we had sometimes we had curves in R2, but they weren't functions. Okay. Now, for something to be a function, we had this thing called the vertical line test. Do you remember that? Basically, we have some curve. So this is our curve we're considering, and we're wondering if it's a function. If we can draw a vertical line through our curve and hit our curve more than once on the same vertical line, then it's not a function. So this would not be a function, right? It fails the vertical line test. Okay. Because we have one vertical line and it hits more than once. It hits 3 times, actually. Okay. Now, maybe you use that and you never really thought about, or you haven't thought recently about why that works. What is the reasoning behind that? Excuse me. Well, remember what the definition of a function is. Okay. For a function R to R, a single variable function, a function, you remember we have this kind of general idea, a function is a rule that pairs each point in the domain with a unique point in the range, okay? Meaning I can only pair, let's say if I have X in the domain, I can only pair it up with one Y, okay, a unique Y. I cannot take that X and pair it to Y and Z. Or, you can think of it as Y1 and Y2. Okay, now I'm no longer pairing X with a unique Y, right? I'm pairing it up with, if I'm pairing it up with 2 different Ys, okay, it's not a function. And that's what this vertical line test is saying. Your vertical line is along some X value, okay? So when you have a curve like this, what your curve is saying is essentially, okay, I'm taking that X and I'm pairing it up with this y, y1. I'm pairing it up with that y, y2, and I'm pairing it up with that y, y3. So that's the reasoning of the vertical line test. Okay, if our vertical line hits a curve more than once, well, that means you're pairing one x up with more than one y. Okay, so not a function. Now we have, we saw earlier in the video that we have a similar definition for multivariable functions. Okay, a multivariable function, let's say R2 to R, I pair a unique point xy, excuse me, I pair each xy up to a unique pair each xy to a unique z. Okay. So it's similar phrasing. Does that mean we have a similar vertical line test? And the answer is yes. And it's so similar that, you know, you can probably, if I didn't tell you any more about it, you could probably do it on your own and figure it out. Okay, so what does our vertical line test look like for these functions or these curves in R3, right? Okay, we're in R3 now for both of these, and we want to know, is this equation, okay, let's work with this equation first. Is this a function from R2 to R? Okay. Let's try a vertical line test. So what I do is I could graph my equation, my 12-6 material. I know how to graph this. Okay, this is what, it's a sphere with radius 3. Okay, so that's what I've drawn on the left side here. Now my vertical line test. Okay, let's just draw a vertical line. Let's draw some vertical line, and imagine it going straight down parallel to the z-axis. Okay, you know, maybe I have some vertical lines out here that don't touch my curve at all, my surface at all, and then I come over here to this vertical line. Okay, what's happening with this? It's coming down, it's hitting my sphere, and then what happens? We could imagine, let's say it's not going to stop. Let's say it's going to go blast straight through. It would go, you know, maybe touch the surface of my sphere here, and then it would go inside my sphere, and then maybe it would come out the bottom, right? But what's happening? It's touching my sphere at this point here and at this point here. In other words, this vertical line touches my my surface at more than one point. So just like with our single variable functions, this is not a function. It fails our vertical line test. So essentially what is happening here is I have XY points, right? Let's say, okay, let's say I have this point XY, and my yellow vertical line is passing through that XY point in that horizontal XY plane where the Z coordinate is equal to 0. Well, this vertical line is saying, like, okay, I'm pairing this point in the XY plane, I'm pairing it up with this point on the curve and that point on the curve. So I'm pairing that same XY up to two different Z values. Okay, so it's not a unique, it's not uniquely paired to one Z value. In contrast, let's try the vertical line test again, but with this equation. Okay, so Z equals X squared plus Y squared. Okay, let's think about vertical lines again. All right, so maybe I have some vertical lines out here that, you know, don't seem to touch it. It probably would eventually. But let's say I have a vertical line here. Okay, and then remember, this is what is the shape? It's essentially like a hollow cone or shell. So I have a vertical line coming straight down, and let's say it's not actually, it's going into the open mouth of this cone. It's going inside the cone. It still hasn't touched yet. Still hasn't touched. And then maybe eventually it's going to hit that wall of the cone and it's going to pierce through. Okay. So my vertical line really only touches at that one single point. All right. So and I could, you know, do the same thing for any vertical line. I have another vertical line. Okay, it's coming down. It's entering the mouth of this cone, still not touching the walls, still not touching the walls, still not touching the walls. And then maybe down here towards the bottom, it finally hits a wall of my cone and pierces through. Okay. But it's still only touching one single point on my surface. So it passes the vertical line test. Okay. And I don't think your textbook even mentions this vertical line test, but you know, we can adapt it for our these functions R2 to R, or these equations, okay, to see if it is a function from R2 to R. Okay. And that was what was going on with our stuff in 12.6. We had all these equations, right? Like we had equations like this, and they give me these surfaces in R3. So all of those equations in 12.6 give me surfaces in R3, but sometimes those surfaces were these like, you know, these objects in R3, but they loop back over on themselves and they fail the vertical line test. So even though they're giving you shapes in that three-dimensional space, even though they're giving you these surfaces, they're not necessarily functions. It's the same exact idea that, okay, x squared plus in R2, x squared plus y squared plus 9, that's a circle, right? So this equation gives you a shape in this plane. It's this circle, you can draw it, but it's not a function, right? Because it doesn't pass that vertical line test. Okay. On the other hand, like something like y equals x squared, you can draw that and it's also a function. It passes the vertical line test. And these are, you know, these two-dimensional shapes are the exact, you know, are the two-dimensional analogs of the equations, or the three-dimensional stuff we just drew. Okay. All right. One last topic to talk about quickly: level curves. Okay, so this is another good way of visualizing functions from R2 to R. And you might have seen something similar before and not even realized it. So what is a level curve? Okay, so sometimes drawing the curves in R3 can be difficult, and we want, you know, maybe a simplification of things, or we don't want to kind of look at some specific data. Okay, so that's when these level curves can come in handy. Okay, so what's the setup? The setup is I have f x y equals z, right? So I have my two independent variables and I have my dependent variable. Right? What I'm going to do to find my level curves, and it's best to just find them and you'll kind of see what they are. I think it's better than trying to explain it now. What we're going to do is we're going to set z equal to some fixed value. So instead of having like a variable, I'm going to plug in this constant c. Okay. So c is like a number like 4, 9, 25, whatever. Okay, so I'm going to plug in a constant c. Now, my level curve, what is my level curve? It's going to be all the points x, y in my in R2 that satisfy that equation. Okay, so it's going to feel similar maybe to what we did in 12.6 with the cross sections, but it's actually going to be different. So what do I mean? Let's just do an example. let's say I have the equation f of xy equals x squared plus y squared. Okay. You could also think of that as, again, you could think of that as z equals x squared plus y squared. Right? All right. So this gives me a three-dimensional, or it gives me a surface in R3, right? I could graph that, and we kind of graphed it up there already, but forget about that for a second. Let's say, let's not even try and graph the thing in R3. I want to find level curves. So what I'm going to do is I'm going to pick a couple values for z. Okay, let's say z equals 0. Okay, my level curve is going to be all the points that satisfy this equation when I plug 0 in for z. Okay, so let's kind of keep track of this. Okay, so I'm picking z equals 0. Then my equation becomes this: 0 equals x squared plus y squared. Okay. Well, if this is my equation, what do x and y have to be? Right. Well, since x squared and y squared are both positive, the only way, or they can never be negative. The only way I can get 0 out is if x and y are both 0. Okay. So there's only one point in the xy plane that will make that equation true. Okay, so here's my xy plane. The only point in xy that makes this equation true is, let's do it in blue, is the origin. Okay. So that is my level curve for z equals 0, and I could label it z equals 0. Okay, not too exciting, and maybe you're not seeing, okay, maybe you're saying to yourselves, okay, what's with the terminology level curve? Let's do a couple more, and it might start to become clear. How about z equals 4? Okay, when z equals 4, my equation becomes 4 equals x squared plus y squared. Okay. Now think about this in terms of R2. What equation is this? Well, that's the equation of a circle with radius 2, right? Okay, so let's graph that. Say that's 1, 2, okay. 1, 2, 2, 2. So now I have this curve here. So that's my level curve for z equals 2. Okay. And I could draw more of those. And maybe you've already spotted a pattern. They're all going to be circles, right? Okay, so the next one, when z equals 9, okay, I have 9 equals x squared plus y squared. In other words, level curve with radius 3, or the circle with radius 3. And I could keep drawing these curves. They're just all going to be circles. Okay. So that's how we make them. Now, what does the name level curve mean? Well, think about it as like, to kind of discuss that, let's kind of think about the 3D picture of this now. Okay. What's the 3D picture of that equation, our original equation? It's that parabola, right? Their elliptic paraboloid. So my graph, my 3D surface is this thing. kind of open cone. Okay, so when I have this, so when I say z is equal to 4, okay, it's like you're picturing, you're kind of taking a plane. It's almost like you're taking a cross section, kind of like we did in 12.6. You're taking a cross section. What is the cross section when z equals 4? Well, it's just that circle, right? Okay, so that's what the cross section is. But the level curve is this cross section dropped down to the xy axis. In other words, it's all the xy values that give you that cross section. Okay. And if I went further up to like level 9, I took a cross section there. Well, again, that cross section at 9 is just going to be, maybe it's this circle. Okay. Okay, and then I drop those values down to the xy plane. And again, it's this circle of radius 3. Okay, so that's what level curves are. Think about it, it's like you're fixing a level of z, and then you're finding all the xy points that give you that level of z. Okay, and if you're looking for like a real world corollary or real world example of something like this, think about, you may have heard that may have heard of something called a topographical map. Okay, so in areas where there's like a lot of elevation changes, like mountain ranges and stuff, how do you map a mountain range on like a flat two-dimensional piece of paper? If you have a map and you're trying to say, okay, well, there's a mountain here and it's really high, and then it kind of gets lower and lower and lower. What you have is like, you may have seen these maps that are like weird kind of shapes inside shapes, these kind of nested curves. And what those are they correspond to different elevations. It's like saying, okay, this outline here, well, that's like an elevation of 10,000 feet. And then this elevation in here, or this curve in here, that's an elevation of 15,000 feet and 20,000 feet. And you can kind of picture, as you get closer and closer to that center, you're getting closer and closer to the peak of a mountain. Okay, that's essentially what these level curves are. Okay, all right, so it's these, you can think of these things as being these elevations, these kind of nested elevations. And maybe they give you a picture of what's happening. And if you can't, like, if you don't draw out your three-dimensional curve, like in this example, this thing is easy to graph in the R3. But maybe if we got something more complicated, maybe we couldn't graph the whole thing in R3. Maybe all we could do is make these level curves. And we see that, okay, as z gets bigger and bigger, or let's see, as we move outwards, as these circles move outwards, our z is getting bigger and bigger and bigger. Okay, so that tells me, okay, I have, maybe it's not enough to get a super clear picture of what's going on, but it's like saying, okay, in R3, I'm here at the center, and as I move away from the center, I'm getting higher up in no matter what direction I go, that's true. So it's like I kind of get these curves like this, and then maybe I can put them all together and get my three-dimensional shape. Okay. So that's the idea behind level curves. It's fairly straightforward. And then we can just scale this idea. Last topic is we can scale this up into 3 dimensions and higher dimensions. But level surfaces. So let's say, what we just talked about for level curves, that's when we had f of xy equals z, right? Or another way to think about that is remember that notation I said we could use. Instead of x and y, maybe I use x1 and x2, and that gives me a y value. What if I have a function of more than 2 variables? Let's say I have a function of 3 variables, f of x1, x2, x3, and that gives me a number output y. Okay, now I can't, this is, maybe when level curves come in handy. I can't graph this, right? Because it's got 3 inputs, 1 output, so the graph would be 4-dimensional. Now, if I just drew a number line and just kind of did the outputs, okay, well, I just get a shaded region of a number line. That doesn't really help me determine what's going on either. So what you could do is level surfaces. Okay, so you could say, okay, let's set y. Let's put a constant over there. So you set c equals fx y x1, excuse me, fx1 x2 x3. Okay. Now, what will this be? This will be an equation in R3, right? So it's something you can graph in R3, and maybe it's like a sphere. Okay. And then you say, okay, this sphere is when fx1, x2, x3, that's when that sphere, or this sphere is when our function equals c. And then you have another sphere, and it's when your function equals 4. And so on. And maybe you see you have these spheres moving outward, and as you move outwards, you get larger and larger values for your dependent variable. Okay, so maybe that sounds confusing. I think the book gives a good example with temperature, right? So let's say you have like a 3-dimensional room. Okay. And you're talking about the temperature inside of the room. Okay, so maybe at this point in 3 dimensions, it's got one temperature, maybe like this is like the hottest point in the room. And then it's getting cooler as you move outwards. And the temperature, maybe the temperature at the point x, x1, x2, x3, maybe that the temperature there, well, the temperature is just a number y, right? So you have like a point, an input of a 3-dimensional point. Okay, you plug in your location essentially, and your output is a temperature. Okay, so maybe you're asking yourselves, okay, where is it 70 degrees in the room? So you plug in like 70 for your temperature, and you graph your function, and you see, okay, well, your all the points where it's 70 degrees is this kind of 3-dimensional, let's say it's a sphere. When you set y equal to 70, you get this sphere around that center point. And then if you set your y equal to 60, you get, the sphere out here. Okay. And so you get these nested, these level curves, these level surfaces essentially. So each of these things is a surface corresponding to some value of your dependent variable. So it's like a 3-dimensional version of the level curves, so we just call them level surfaces. That's really it for all the material in 14.1. Interestingly, I kind of what I've been saying in the videos from time to time about how to interpret these functions and how to interpret the difference between vectors and points and things like that. They kind of talk a little about that, and maybe a little bit more more relatable to you is this discussion that's on just the last page, basically the last paragraph of section 14.1. It's how you can think about these multivariable functions. And they give three ways to think about them, and they're all equivalent, but it's kind of helpful to be able to think about all of them. So if I have fx, y, and really, we don't have to talk about 3 dimensions. We could talk about n dimensions. So let's say I have a function of fx1, fx2, dot, 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 all the way to xn. There's a couple ways to think about this. You could think about this as a function having n different inputs. So you have, each of these is a number. You have n different numbers, and you plug them into this function, and you get one output, right? One output, which is just a number. Okay, so that's one way to think about it. Another way to think about it is, okay, instead of thinking about this as just n separate numbers, you could think about this as a point in the space Rn. So for example, if you had a function R3 to R, okay, so what would it look like? You would have something like x, y, z equals alpha. Okay, so you could think of this function as having, okay, its inputs are the numbers x, y, and z, or you can think of it, okay, this function has an input of the point x, y, and z, meaning like you have three-dimensional space. What's going on? You have three-dimensional space, and then you have this object, this single object, the point P, which just has coordinates x, y, and z. You take this point and you plug it into a function, and it gives you the value, whatever, alpha. So it's like it's assigning this point to this numerical value alpha. And then the third way to think about it is, instead of a point, think about it as a vector, which I've already said, I think of points and vectors as essentially the same thing. They make the distinction of, okay, you could think of this point as its position vector, which is the vector starting at the origin, ending at the point. So you could also think of this function as having a vector input, numerical output. That's really it. And that's it for section 14. There's some terminology. I looking at this textbook, I didn't cover all the terminology. Let's see, maybe some, and I don't know how important it is to you. You can look at section 14.1, and I saw, okay, there's some terminology in here. Linear function. That's in example 5. And I would also look at the half space. I won't go over them here. We'll end the video there. But if you have a little extra time, look at these terms. It's not going to be critical to this course, but if you go further in math, you'll probably be hearing these a lot, especially like linear function. If you take 3105, 3106, or differential equations, you're going to be talking about linear stuff a lot. And the half space, yeah. Look those up if you like. Good luck.